Okay, so and everyone see that in presentation mode?
Yep, you're good.
Yep. Okay, good. So this is work with Ryan, who's the one chairing the session. So also with Nathan, who's now at University of Toronto, and Junho Lee, who is doing the numerics for the quantum chemistry part of this. So essentially what this work is on is looking at more efficient ways of simulating the realistic the chemicals in general bases. So there's the archive number shown there. Yep, can you see the cursor for pointing?
Yeah, I can.
Yeah.
Yep. Okay, good. So the general motivation for these types of things are that if you can simulate the chemicals, then you can possibly be using simulation to more effectively design things for particular applications. So the pictures that are shown here are for drug design or batteries, or this one is for fertilizer. So the idea with the fertilizer is that fertilizer is produced using nitrogen fixing, and there's a very inefficient nitrogen fixing process, but the biological nitrogen fixing process is much more efficient, and that's based on a chemical where the active site's called FOMOCO, which is quite a large collection of the atoms, which includes some fairly heavy atoms, which makes it quite difficult to simulate in comparison to smaller molecules, which can be simulated far more efficiently in a classical approach. And generally, the complexity of the classical methods scale up exponentially with the size of the system, whereas with the quantum computer algorithms that we're developing, that's always expected that it's going to be something which is the polynomial in the size of the system, but there's a big challenge in actually constructing something which is going to have a small number of gates that can be realistically performed on a quantum computer. So that's essentially what we're doing, is mapping it out to a sequence of gates and estimating about how many non-Clifford gates you'd need in a fault-tolerant implementation. So more generally, we're interested in the scaling of the complexity as we go to larger systems. So there's a couple of columns here. One is what's called the thermodynamic limit, which is the scaling as the size of the system is growing. So the n here, that's the number of orbitals. So orbitals are essentially like the pattern of the probabilities for a single electron, and you have multiple orbitals. And when you have a multi-electron system, you look at how many, which orbitals are actually occupied by electrons. So for cases of interest, n is going to be around on the order of 100 to 200, which isn't enormous, but still, if you have complexities which are scaling more than n to the 5, then that's going to end up giving you a very difficult algorithm to implement. So this one up the top here is one that we developed in a paper in 2016, and there's a whole sequence of improvements, and this one here is n to the 2.1 according to our estimates. So that's also an improvement over some very nice work from the Microsoft group last year, which we estimate goes as n to 3.4. The other case is where you're increasing the precision of a simulation on a fixed system just by increasing the number of orbitals. So increasing n, but just still looking at the same system. And typically what we find here is that the scaling with n is worse, and we get a scaling of about n to 3.1 here, which is still better than the scalings of any of the other previous methods. So like I was saying before, we're counting non-Clifford gates. So the reason for this is that what we're interested in doing is looking at a eventual physical quantum computer which has error correction in the surface code. And of course, it's not possible to do every gate that you need for universal quantum computing natively in the surface code. And you have things, Clifford gates, which are easy things like C-naughts and X gates, which are easy in the surface code. But if you want to do a non-Clifford gates, which are things like T gates and Toffoli gates, that's just controlled C-naughts, those are much more difficult, and you want to distill magic states in order to be able to do those. And a lot of the time in previous work, it was just looked at counting T gates, but in our work, there's basically no T gates we need, and it's all Toffolis, and it's possible to directly distill the magic states for Toffolis, so that's the way we count our efficiencies. Now, the general method that we're using here is, well, it's related to the block encoding that Lin was talking about just before. So the general idea is that you have a Hamiltonian, which is described as a linear combination of unitaries. So you have weights WL and unitaries HL. And the important feature of this, which I'll be going back to again and again, so is the lambda value, which is the sum over the weightings. So generally, there's going to be various different ways of representing the Hamiltonian, which are going to give you different values of lambda. So we want to choose a representation which makes this as small as possible. And that's because the complexity in terms of the number of steps ends up scaling linearly in lambda. And the individual steps that we're using are generally constructed in this way. So the part that you see here up to the R is basically a block encoding of the Hamiltonian. So if you were to put a 0 state in here, and then this is a P for a preparation, then you do a controlled H, then you do an inverse preparation. If you were to post-select on a 0 here, that would be a block encoding of the Hamiltonian. But in qubitization, what you're doing instead is to do a reflection about 0. And that operation altogether gives you an operation which is effectively like a function of the Hamiltonian. And when you want eigenvalues of the Hamiltonian, which is typically what we want to estimate ground state energies, you can just do phase estimation on W and just invert that arc sign to get the eigenvalue of H. And that's much more efficient than trying to generate the Hamiltonian evolution, which is what was done in a prior work before there was notice that you could do this. Now, the particular type of Hamiltonian that we're interested in here is the electronic structure Hamiltonian, and that typically, in the general case with general orbitals, looks like this. And the idea of choosing general orbitals is that you can choose a set of orbitals where you can accurately represent the system with a relatively small number of orbitals. So there's other approaches using plane waves where you need a large value of n, and you can simplify the Hamiltonian. But when you're using these general orbitals, you end up with a form like this. And here the A and A dagger, they're creation and annihilation operators for electrons. And the overall complexity is going linearly in that lambda value, which I mentioned before. And it tends to scale with the amount of data that's needed to represent the Hamiltonian as well. But in terms of the non-Clifford gates, it tends to scale like the square root of the amount of data. So it's not as bad as linear, but still, if you're looking at something like this, where there's order n to the 4 terms, then that's going to end up being a pretty inefficient simulation. So one approach that we looked at before was essentially looking at the actual values of these V's and T's that you end up with. And it turns out that for FOMOCO, there's a lot of these that end up having very small magnitudes. So what you can do is essentially just pick out the values of V that are significant and use those in the simulation and ignore the ones that are very close to 0. And we obtained a dramatic improvement in the complexity using that approach over prior work, which was basically using product formulas. And the general idea there was just that it was reducing the amount of data that was needed to represent the Hamiltonian. But drawback to that approach is that if you're thinking of sort of what's the scaling going to be with larger and larger systems, there's not really a good general theory for that other than just trying to do numerics on examples of systems. So in that same paper, what we did was look at a factorisation approach. So the idea there is that this first term, so that's a electron-electron interactions, and that's the largest, and just because it has, you see, that's summation over P, Q, R, and S. So we don't worry about the single electron one, we do a factorisation on the 2-electron one, and basically you have this rank here, which is L, which would be n squared to give you something here which is exactly the same as here. But it's found that this L can be truncated to order n in practical cases. So what you end up with then is these GLPQs, which are encoding the majority of the information in the Hamiltonian. And because the L and P and Q are scaling over order n things, then that's order n cubed parameters instead of order n to the 4th. So that gives a improvement in the asymptotic complexities. Now, there was another approach which we suggested in that paper but we didn't analyze, and that's the approach that the Microsoft group with von Berg analyzed, and they came up with a whole lot of extra clever ideas for reducing the complexity there as well. So the general idea here with this double factorization is that that thing that you're seeing in the large brackets there, that's factorized as well. So generally what you can do is change the basis of orbitals with these UL operations, and then this thing inside the brackets, that ends up getting diagonalized. So instead of having A dagger P AQ, you'd just have A dagger P AP. And so these G's are being replaced with H's, and there's far fewer of these H coefficients than there are of the G's. Well, that's the general hope. But the other thing is that this ends up giving you a reduction in the lambda value. So that's the main advantage that's put forward in the von Berg paper, and they also had some other tricks for reducing the lambda value there as well. Now, the representation we're using in this work is to use what's called the tensor hypercontraction approach, or THC. So that's an established method in the classical literature. So there's an example down there, and the representation basically takes this V and represents it in terms of chi's and zetas. So the dimension of these things, the chi is going like an n times m, and the zeta is going like an m times m. So m is this truncation for the THC representation. And surprisingly, it turns out that you can take that to be order n typically as well, which gives you a number of parameters which is just scaling like order n squared. And so if you were to then translate this into a linear combination of unitaries, you'd get a lambda value which scales like this, but this turns out to be larger instead of smaller like you'd get with the double factorization approach. So if you were to do it this way, you don't actually get a more efficient algorithm. So then what you want to do is try and rearrange this to reduce that lambda value to give you a more efficient simulation while still maintaining that small number of parameters that you want for the efficiency as well. So this is the general idea, is that you group together these summations like this. So just to remind you, we had all these summations over P, Q, R, and S over here. So we've shifted them over and put them on the chi's. So you have these summations over chi's, A dagger, chi, and A. But when you have a summation over creation or annihilation operators with weightings, and that's basically like a change of basis. So you can define these new creation and annihilation operators, the C mu and C nu here. And these are now going to be sensible fermionic creation and annihilation operators individually, but when you look at them all together, it's a bit of a problem because you now have m of these and not n, and these the modes that they're corresponding to aren't actually orthogonal anymore. So that's a problem, because if you're wanting to, say, do a unitary transformation to transform between bases, that's not going to work when you're dealing with a non-orthogonal basis. So this is quite a problem. Well, it looks like quite a serious problem at first sight, and it looks like you'd need to have some scheme for doing non-unitary transformations to transform to the C basis. But the trick is to notice that you have a summation over mu and nu here. And when you're translating this into a linear combination of unitaries to implement this the cubitization approach, then you are only dealing with one of these parts in this sum at once. So each of these parts in the sum is going to be a parallel part in the superposition, and you can deal with these independently. And that means that you can do individual rotations to these individual orbitals in this C basis without worrying about the other orbitals in the C basis. And if you're only rotating to one of these at once, it doesn't matter that the other ones are non-orthogonal, because you could imagine that there's another set of imaginary orbitals that are orthogonal to this one. And another advantage of doing it like this is that these rotations that you want to use to transform to this new basis, well, generally to actually implement these, you're taking these rotations and decomposing them into simpler two orbital rotations called Givens rotations. And to do a general transformation, you'd need order n squared of these. But when you're doing it on each of these individually, there's only order n. So that's something which was found in the von Berg paper, and we find the same thing here. So, but like I was saying before, the main thing that we were aiming to do, expressing it like this, was to reduce the lambda value. So that initial lambda value, that was a 6-fold summation, and it's just reduced to this 2-fold summation. And generally when this is happening, you have a lot of cancellations in between the terms, and this 2-fold summation is going to be a lot smaller than this one. And we actually find that for the case of Fumoko, that our lambda value is about the same as for the von Berg paper, and also that we expect that there's better scaling for larger systems. So that's what's shown here. So there isn't really a good theory for the scaling of these things in terms of the value of lambda, but what we've done here is look at a sequence of the simple systems. So this here is a chain of hydrogen atoms, and so that's looking at the thermodynamic limit. So remember, that was a growing system size, so it's a chain with more and more hydrogen atoms. And this one is a continuum limit. It's looking at more orbitals for the one system. So I'm a little bit short of time, so I'll just talk about this one. So what you find here is that this line down the bottom, that's for THC, and that has the best scaling in terms of the scaling up to larger values of n, because it has the smallest slope there. So we're getting lambda going as n to the 1.11 there versus n to the 1.88 for the double factorization, which is the next best one here with the red triangles. So to actually implement this in the quantum computer, we're using a representation, and similar to many previous works, where we have each orbital corresponding to a qubit, and the qubit is 0 or 1 depending on whether that orbital is occupied by an electron or not. And then you can take these annihilation and creation operators, translate them to Majorana operators, which are anti-commuting but unitary, and then those can be represented on the qubits by chains of the Pauli operators. But we only actually need these number operators, and these number operators, they just turn into identity minus z. So that summation where we had number operators, basically those get turned into z's, and this identity, that can be put into the one electron part of the Hamiltonian and combined with that. And I won't have time to talk about the controlled unitary. I'll talk a bit about the ideas of the quantum ROM, which is used to output the rotations for these change of bases. So the general idea was that we want to have these sequences of Givens rotations in order to rotate the basis. And each Givens rotation, it has to rotate by a given angle. And the idea which we're taking from the von Berg paper is to use a quantum ROM to output the rotation angles that are needed, and then use that output to control the Givens rotations to transform the basis. So the quantum ROM is essentially taking an input register and outputting some classically chosen data based on that input register. So that's, if you have L encoded in an input register and you're outputting classically chosen data DL, and these C naughts here are indicating that there's either, with question marks, are indicating there's either a C naught or not a C naught to output this individual items of data, D naught, D1, D2, etc. And this circuit is able to basically control on 0 here, then control on 1, control on 2, control on 3, and so forth. And these left and right elbows are basically just indicating Toffolies, where there's an extra trick where if there's a Toffoli where the output is guaranteed to be 0, that can be done with measurements and Clifford gates, so it doesn't add to the non-Clifford cost. Then we have another approach which we use for the state preparation. So remember, in our qubitization approach, we need to do a state preparation to prepare a state with weights that are corresponding to the square roots of the weights in a linear combination of unitaries. But it turns out that these are allowed to be entangled with ancillas. So the general idea to make this state preparation efficient is to, instead of preparing something like this, you prepare something where it's entangled with an ancilla. So what you do is you start off preparing an equal superposition over these L's, and then you use a quantum ROM to output alternate values of L's and keep probabilities. And the idea is that you're going to swap these two registers with the L and alt L according to the keep probability in a coherent way. So you're doing an inequality test with an extra register and a swap based on the inequality test. And that's like alias sampling for generating classical probability distributions. But when we're doing that for the state preparation, that is actually needing a lot of data to be output. But there's another trick which is from Guang Hao and co-workers for improving the complexity of this QROM. So the general idea is you're taking your input register, which is shown as X now at the top here, and you're separating that into low significance bits and high significance bits. And based on the top ones here, you're outputting data indicated as these X's here for every value on the remaining qubits. And then on the remaining qubits, you use those for controlled swaps, which then can swap the data that you want into the correct output register. And the neat thing about this is that when you choose your subdivision of these qubits appropriately, your complexity ends up going like the square root of L, which is the number of items of data, times an M, which is the number of bits for each item of data. So if you're thinking about the total amount of classical data, that's essentially L times M. And you have a complexity which is scaling like the square root of that total amount of classical data. And that's why we get a complexity which goes like the square root of the data that's needed to represent the Hamiltonian, because we're using this advanced QROM for the state preparation, and the state preparation depends on the coefficients that are used to represent the Hamiltonian. So I think I'm supposed to be finishing in about 2 minutes. Is that right, Ryan?
Yeah, that'd be good.
Yeah. So I've there is various subtleties here which I'm kind of running out of time to explain, where we're choosing particular numbers of bits to represent things and a particular cutoff for the M, and it can be numerically estimated what the appropriate cutoffs are. And then for the case of Fumoko, we estimate that for the original orbitals given by Ryer, you can get away with about only 5 billion Toffolies. And just to compare this with other methods in this table, here we've actually recomputed the complexities for other methods using similar assumptions, and the von Berg method actually has a complexity of about 10 billion Toffolies, which is slightly better than the estimate in their paper. And our method for sparse Hamiltonians had about 44 billion as the complexity. So when we're looking at the case of this particular example, we're getting the best complexity as well as the best complexity of the scaling. So the complexity of the scaling basically comes from looking at taking the scaling of the lambda values. So just I'll just concentrate on this part here where we have the n to the 1.11 for the scaling of lambda multiplied by the square root of the amount of data. And the amount of data with the THC representation was n squared. So this is basically just giving you another factor of n here. So you're getting about n to the 2.1 for the scaling of the complexity. And it's this approach that we use to generate all of these asymptotic scalings in this table. So I have some other slides here which I don't really have time to go over, but I can go back to them and explain them if people are wanting to ask questions about them. So essentially the conclusions of this are that using this representation, a temperature hypercontraction, we get the best efficiency yet for simulation of quantum chemistry, both in terms of the particular example of Fumoko and the scaling for larger systems. And the two reasons why this efficiency is high is because you have a small value of the lambda norm for the Hamiltonian, and at the same time you're representing the Hamiltonian with a small amount of data. And I'll just quickly point out the archive paper down the bottom there. Okay, thank you. And we have time for questions, do we, Ryan? Or do we need to go to the next? Or
no, this is the last. This is the last session, so I think we can take. We can take at least one question. Does anyone have any questions?
There's a sound that sounded like someone typing something in the chat, but I can only see my presentation screen here. I can't see the actual...
I tried raising a hand, a digital hand.
Please, Earl.
Hi, Dominic. So I was just going to ask, so you mostly talked about what different factors that affected the kind of Toffoli count, but the number of logical qubits in that table were quite different between the different schemes. So, I mean, if I remember correctly, the tensor hypercontraction uses some extra qubits in the like some extra orbitals, but so then it ends up using fewer in total than double factorization.
Yeah. So there's actually, this is like that's a very nice question, because now I've got an excuse to go to the slides that I skipped over.
Okay.
So basically, this here is what's showing the usage of qubits for that a Toffoli count that I gave first. So this is showing sort of as you've got running through the algorithm, and this is like each step in this direction is how many Toffolis you're using, and vertically it's showing how many qubits you're using. So this first part here, that's for the state preparation at the beginning, which is using that advanced QROM from Guanghao that I mentioned. So that advanced QROM, you have a choice there of how you divide things between the high and low sets of qubits. And if you choose it to optimally minimize the number of Toffolis, it needs quite a large number of qubits. So that's the qubit counts that are shown in this table for minimizing the number of Toffolis. But if you want to use smaller numbers of qubits, you can change the parameters there and dramatically reduce the number of qubits at a moderate increase in the number of Toffolis. So in this example, we have a k equals 64, which is quantifying how the subdivision between the Toffolis, between the qubits goes. And if you reduce that to 16, you have this instead. So you see, vertically, it's only something less than 700 here, whereas it's going up above 2000 here. And the other part where you're using a large number of qubits is where you're outputting the data for the angles of rotations you want for the given rotations. So that's what's shown here. And so here you have this, the orange part where it's outputting that data, and then it's using that data when it's doing the rotations. And this funny triangle here is where it's basically using up that data, and it can just discard the data as it goes. So it's reducing the amount. But basically, this is outputting all of that data at once. And here you can just output the data in two parts. So you output the first half of the data, do the rotations for that, output the second half of the data, do the rotations for that. And then this part here is outputting the data for same data as this one, because when you're outputting the data here, you're having to overwrite the data here. And so that also needs more Toffolies, because you're outputting the data basically in 3 times as often as you were before, but it's halving the number of qubits you're using there as well. So that's another trick that we're using for reducing the number of logical qubits. And so then we estimate that if we had about a 0.1% error rate, that this could be done on 4 million physical qubits, which is quite large, but it's still pretty competitive compared to other methods. So the other methods, they're also using large numbers of qubits, you can see here, and you can look at various tweaks there as well for trying to reduce the numbers. I think that's it.
Thanks, Dominic.
Maybe a longer explanation than you were expecting.
Yeah, I think that's probably all we have time for today. Yeah, again, thank you for the talk. And Tom, is there anything else you want to say to wrap it up?